You already know about anions from back in Chemistry 1210, Chapter 4, and you already know about temperature effects on solubility from Chapter 17. What I've done here is broken this into pieces. Our part 1 is the presence of common ions, part 2 is solution pH case by case, and part 3, which is possibly the most challenging, is complex ions. But let's do common ions first. There is a trend for common ions. This is the data for sodium fluoride and what happens when we add different amounts of calcium fluoride to sodium fluoride. As you can see, it is most soluble when it is very, very, very dilute. So it says the solubility of a slightly soluble salt is decreased by the presence of a second solute. Here's the second solute, and it furnishes a common ion. So what's included in this section is calculations for molar solubility of calcium fluoride. If I put a common ion in of calcium, or if I put a common ion in of fluoride. So let's get started. By the numbers, whether I have calcium or fluoride, it is going to reduce the solubility of calcium fluoride. It's going to shift the equilibrium to the left by Le Chatelier. So we're allowed to say that the solubility of a slightly soluble salt will decrease in the presence of a common ion. It gives more undissolved solid, it's lower concentration of ions. Those are all the word problems. So before I actually do the common ion, let's look back at the actual calcium fluoride solubility. The KSP would be 3.9 times 10 to the minus 11. Calcium 2 plus times F minus squared, and there are the numbers. Let's now add a common ion. Let's put in 0.01 molar calcium nitrate. We have two simultaneous equations in solution. The first one is the 100% dissolution because it is a strong electrolyte producing the ions. The second is the KSP expression. We are putting in 0.010 molar calcium 2 plus. You know how to make an ice table from the earlier chapters, so you know that in the change line we will be putting in values of X. We will come up with an equilibrium line, and there is nothing here because solids do not occur in the equilibrium expression. So there's our equilibrium expression, and on the next page are the numbers. KSP, calcium, F minus squared. Here we have our 0.010 plus X and our 2X. We will ignore the X as we have in the past, and we will go through and we will do the math. So we come up with a 10 to the minus 5th molar solubility. Many of you have said, can I really ignore the X? Yes, you could do the percent ionization, but think about it. If I have 0.01 molar and, as someone said to me earlier, we are subtracting this amount, what will happen is we will have a number where it is not going to play a role, okay? You can check to be sure you can ignore X, but trust me, for our class you can. So our molar solubility is 10 to the minus 5th molar, but our actual solubility in grams per liter is 2.43 times 10 to the minus 3 grams per liter. Make sure you can differentiate between these two. So for this problem, we added additional cation. For the second problem, we are going to add additional anion, and it's a carbon copy. We just have the number sitting in a different spot on the ice table. I have my equation number 1 that describes the strong electrolyte. I have equation number 2 that describes the KSP expression. Take the time to make the ice table your first few times, depending on where you are when you take the exam. You may come right down to this line. I don't know where your thought process will be, but for a lecture, I want to lay everything out. The change line is as we have done in the past. It gives us, again, an equilibrium line. Again, no solid in the expression. There is our KSP equation. On the following slide, we have the math. I have placed in the expression for F minus. I am going to ignore the 2X. Please remember, there is a square there, and that's going to make a difference in your numbers. When we calculate it out, 3.9 times 10 to the minus 4 molar. That again is the molar solubility. It's in molarity, but someone may ask you for the plain solubility, which is in grams per liter. So that's a typical mid problem. You have a slightly soluble salt, you add some common ion, it will shift the equilibrium to the left and make the solid less soluble. I know the question someone will ask, will we add both of them? No, we will not. We will just do one at a time because as you can see, working through the problem takes a little bit of time. So the bottom line for this section is, if I put a common ion in with a slightly soluble salt, I will decrease the solubility of that salt. Could be a word problem.